Hello, 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 testing, testing, testing. Hello. Testing on X. We can hear on YouTube. How's it going? James McLean and Open Room XYZ and Mark B. Double check that the microphone is working fine. Let's turn this up. Test, test, test. All right. X works. Let's test YouTube. My YouTube is broken on my phone. All right, there we go. Test, test, test. All right, looking good. Looking good. How's it going, Majetti? How's it going, Juan June? All right, we got a fun one for you guys today. Let's get this started. Welcome to another Hoopo stream. This one's called Autoscaling Inference. We're going to be centering this stream on this paper out of ByteDance, Taming the Chaos, Coordinated Autoscaling for Heterogeneous and Disaggregated LLM Inference. This was recommended in our Discord group, and if you haven't joined, you should definitely join. You can post papers and we can end up talking about them. The way that I found the other papers that will be kind of tying into this paper is actually slightly different. So this week what I did is I actually tried to use LLMs directly. So I basically asked, hey, find me 5 recent but seminal papers related to this. And then I asked it to all of them. And wherever I found kind of like duplicates, then I figured those must be good papers, and that's where we got the papers. And if you're here for the first time, all the docs for every single one of these streams containing all the links to these papers and all the links to the various other kind of like visualizations that I show are on this Hoopo docs GitHub, and they're organized such that you can just go to the last one here, Autoscaling Inference, and there you go. How's it going, Ed? All right. So starting with this paper is released 27th of August, 2025, and this paper is about inference, right? Which is basically using a language model to actually do something, right? So whenever I'm here and I type something, what is the color of, I don't know. We'll see. What is the color of? Right there, that just created this effectively cascade in the background, right? There's machines that are connected to me via the internet that basically went through this somewhat complicated process of like routing that request into some GPU and then producing the tokens and then sending those tokens back to me. And this stream is about that story, right? And that sequence of events that happens very quickly in the background without you really noticing. So this is sometimes called inference if you're talking about the actual, what the LLM is doing, but sometimes people also call it serving, right? Because from the perspective of the company that is providing the inference for you, they're serving your requests, right? So they're serving you, kind of like a servant. All right. So we're actually going to start with some of these earlier papers because the paper that we're reading is very recent, but then there's a couple earlier papers you can see. These are from kind of earlier in 2025 that I think present the problem a little bit easier. So LLM inference requests can be divided into interactive requests that have tight SLOs on the order of seconds and batch requests that have relaxed SLOs in the order of minutes. So we're going to need to maybe define what SLO is. SLO is a service level objective. A service level objective, SLO, gauges the proportion of requests fulfilled within a time frame, right? So it's basically you have metrics based on some PMs, basically this is a hyperparameter that some PM is going to choose, right? But these have been tuned, right? We've had lots of different internet-based services for decades now, so people have a pretty good idea of how fast your request should be filled, right? Like whenever you click on something, like how fast is the user going to expect the return, and what percentage of those should fail, and so on, right? So it's not like we necessarily need to pick those hyperparameters just first time ourselves. These have been tuned and adapted for non-LLM based services over the internet for a long time. But let's go back to here. Okay. In this particular paper, they present Chiron, a autoscaler that uses the idea of a hierarchical back pressure estimated using queue size, utilization, and SLO. And the keyword there is this kind of idea of autoscaling. So let's go to this one here. I'm going to be jumping around all these papers. It's like the individual contribution of each paper is not super important. Really, we're just trying to get a good idea of what autoscaling inference is about. And all of the papers are actually kind of very similar, and they all kind of present similar ideas. So if you're confused about which paper we're on, it doesn't really matter. They're all kind of saying the same thing. SLO is a parameter. I thought you just want to be as fast as possible. You have to choose, right? Because I guess, okay, so SLO is an objective, not a parameter, right? So I guess that's true. It's an objective, it's a goal. Theoretically, if you served every single user instantaneously, that would be your perfect objective, but you're never going to reach there. So at some point, you're going to have to kind of decide on a trade-off here, right? And I think one of these actually kind of presents that in a nice way. We'll get to it. I think there's a nice explanation of what the difference there is. Okay, let's go back here. Actually, let's start with this one. This is the survey paper, right? So another way I could have actually done this is actually gone to a survey paper like this, and these survey papers basically find all the relevant papers for you, right? Let's go to I wanted to answer Ed's question, and there's a good answer to it somewhere here, but it's going to be pretty impossible to find it, to be honest. Okay. SLO also ties into SLAs. Maybe, I'm not even really sure what SLA is. What's it, SLA? SLA salad? SLO. Service level agreement is a formal agreement with a customer defining service commitments, including penalties for non-compliance, while SLO is a specific internal, more stringent target that helps service providers meet or exceed. So, okay, it seems like apparently there's SLIs, service level indicators. Okay, so there's whole like mess and tangle. It starts to maybe even get into legal situations where, hey, if you're Amazon and you're providing GPUs to then a company that's providing the AI on top of that, and then you have a company that's using that AI company to provide AI to their particular product. So you have this kind of like cascade of like, hey, we promise this works 99% of the time, and your user's going to get an answer within 100 milliseconds. And then that has some other agreement with a person behind it. But I don't know. Okay. I kind of got lost here. You guys got me just yapping. Okay, here we go. This is probably a good one here. GPU shortage. Deploying LLMs in cloud environments with diverse types of GPUs is crucial for addressing the GPU shortage problem. Okay, so one of the problems that we have right now is that all of our clouds are not one homogeneous type of GPU, right? They're basically many different types of GPUs all hooked up, and these different GPUs have different connectivity between them, right? So one easy way to represent a data center or a group of GPUs is with this idea of a graph, right? So you have all these little GPUs connected in this graph, and once you put something into a graph form like this, you can apply all this math that has been developed for graphs on that problem, right? Similar to how if you can frame your problem within a Markov decision process, then now all of a sudden you can kind of leverage all this work that people have done on this Markov decision problem formalism, right? The graphs are very similar to that, where it's like if you can figure out a way to make your thing a graph, then there's all this stuff that you can apply to it that allows you to optimize it. And in this case, for at least this paper, it's about figuring out how to organize and spread the work into this graph of GPUs such that you meet those SLOs, right? AKA, try to get it as many responses in as fast as time as possible with the least amount of mistakes and in the most efficient way, right? And that last one is pretty key, right? Because even though there's the SLO here of like, okay, we want to make sure that we fulfill our user requests, you also don't want to be, that's not necessarily the most important thing, right? Making sure that your customers have fast and low latency responses is important, but you also don't want to be just like burning GPUs for no reason and having a bunch of GPUs that are allocated that are not really being used, because those are GPUs that you could use for training purposes. So that's kind of one of the driving requirements here, is that ultimately there's this kind of shortage of GPUs. So you can't just naively have a bunch of GPUs for inference and then only 20% of them are getting used at any one moment, right? You want to be able to allocate basically the minimum amount of compute required to actually do the job that you need to do. All right. And you can see here, obviously different types of GPUs have different costs, right? So if you can route something to a cheaper GPU, it's going to be worth it, right? So you can see here A100s, $1, $2 an hour, 3090 Ti's, $0, $3 an hour. Let's go back here. We're going to be bouncing around a lot. I'm already confused. Okay. Maybe let's talk about the most important part of this idea of modern prefill decode disaggregated architectures. Okay. Heteroscale is a coordinated autoscaling framework. This is the same word, autoscaling again, combines topology-aware schedule. Topology-aware just basically means that your schedule is aware of this graph, right? This graph, as we showed it before, right? That is the topology, right? The layout of the landscape, in this case, the landscape of the GPUs and how they're connected in your data center. So topology-aware scheduler just basically means a scheduler that can adapt to the heterogeneous hardware and network constraints within a novel metric-driven policy. Okay. Jointly scale prefilling and decode pools, right? So prefill decode, you have different pools for that. And in this case, for the ByteDance paper, they're using this auto-scaling on tens of thousands of GPUs. So some of these papers are a little bit more kind of researchy, right? They don't really do it on a huge cluster. They're kind of more just talking about kind of the theory of this kind of auto-scaling. But this one here has a little bit more weight to it because it's coming from ByteDance and it's coming from a team of people that are actually trying to serve lots of requests on tens of thousands of GPUs. So we know that this works. Right, they have here increasing average GPU utilization by a significant 26 percentage points. But we learned from some of these other papers that GPU utilization is not really necessarily the best metric. There's ways that that metric can actually confuse you and make you think that you're utilizing your GPUs optimally, but you're actually not. So we're going to actually see how the metric that you choose to optimize here with these schedulers is actually quite important. And GPU utilization is not one of those good metrics. So it's kind of weird here that they actually advertise this when then later on in the paper they mention that it's actually not the best metric to optimize. Okay, so let's go. I think let's talk about prefill versus decode. Here we go. PD disaggregated serving. LLM inference consists of two distinct phases, prefill and decode. In the prefill phase, the model processes the entire input prompt in parallel, building KV cache for all input tokens in one go. Then, the decode phase operates autoregressively, generating one token at a time while relying on the previously created KV cache. Okay, so in order to understand what's going on here, we're going to have to take a little step back and look at what exactly is the KV cache and how exactly do autoregressive models, what is the expression of the compute that they require to produce an answer for you. So here's a blog post by Hugging Face on the KV cache, and here we have a kind of a standard demonstration of an autoregressive transformer with an attention matrix here, where you have a sequence of tokens, and in order to produce the next token, you see how basically you keep increasing the size of this attention, right? This is that quadratic scaling, and that little yellow flash shows you computation that's happening. So here you can see that every single square inside that attention matrix needs to be computed, right? So you can see how as your sequence length grows, you keep having to do a lot of you keep having to do more and more and more computation, right? And that's not great, right? And part of the reason why that can be improved is because actually a lot of that computation can be reused, right? So rather than every single time you create a new token or you have to predict the next token, redoing this particular part of the attention, you could actually save that from the previous step and now reuse that. So you've turned something which requires a lot of computation into something which requires some amount of memory and then computation, right? And the KV, maybe more specifically, what is the KV part of it? And for that, we're going to pull up this nice little 3D visualization of a transformer that I've used plenty of times before. And you can see here it's a repeated pattern of 3 blocks, right? These are the 3 transformer blocks. And then if you go into the transformer block, you kind of have 2 parts here. You have the feed-forward network, which is just your standard multi-layer perceptron, right? The neural net of old. And then you have this kind of more modern part here, which is the actual kind of attention operation. And in this attention, you can see that there's multiple heads. That's what these 3 bunches are. And inside each of those heads, you have these V weights, K weights, and Q weights, right? And in order to see how those are used, we kind of have to go to this view, and you can see how there's a green arrow here that goes between the Ks and the Qs, right? So your keys and your queries, and that's going to actually create your attention matrix, right? Then your attention matrix can go through that softmax, and then you can see that now it's going to be interacting with this V, which is your values, and then you're finally going to get this V output here, right? So whenever we're talking about KV caching, what are we actually caching? We're basically caching the values in here, right? Because whenever we have a new token, what's going to happen is we're basically going to have a new kind of row here, right? Or a new column. I don't know exactly which dimension is which in this visualization, to be honest. But in order to get that new row or that new column there, you don't actually need to recalculate all these things, right? Because all the previous parts of your sequence are still the same, right? The first 4 words of your sentence are still the first 4 words of the sentence, whether you're trying to predict the 6th word or whether you're trying to predict the 10th word. So caching those basically just means you take this thing here, this little V output, and you save it on memory, and then next time you create a token, you use that already existing stuff in memory rather than recomputing it, and that saves you compute, right? So fundamentally, prefill is a high compute-intensive phase and benefits from substantial parallelism. Decode is inherently sequential and less demanding in raw computation. Prefill's memory footprint grows with the length of the input prompt, while decode's memory demand increases with the size of the accumulated KV cache, right? So prefill is, okay, I sent you this is a relatively short prompt, but imagine I sent you a paragraph of text. And that's what I'm sending for my inference request. So getting that paragraph of text and doing this right here, right, creating this KV cache for every single part of that text, that's the prefill phase, right? And the reason you can do that in parallel is because these don't depend on each other, right? you could kind of do them in parallel because you have the whole paragraph is getting sent to you at the same time. But as soon as you start decoding, which is now actually creating the tokens that are going to be in the output, now then you kind of hit that autoregressive wall, and you have to basically wait for the next one and wait for the next one and wait for the next one, right? So that's why this decode is inherently sequential, right? But it's inherently sequential, but it's less demanding in the computation because you don't have that giant attention that you're doing. And that's actually one of the important parts of this, right? Is that, for example, here's a nice example. The A40 GPU with 149 teraflops is more cost effective for the compute intensive prefill phase, whereas the 3090 Ti with 1000 gigabytes per second memory bandwidth is better suited for the memory bounded decode phase. So decode, because we have to go back and retrieve values from this KB cache that we stored, it's more memory intensive, right? So you can start to see how this is, we're painting a picture of a relatively complicated problem here where, hey, you have different GPUs that have different memory bandwidth versus actual flops, which is like, think about like the actual cores in the GPU. That's basically this, flops here, versus the memory access bandwidth is like how fast can you bring information and take information out of those cores, right? And they have different prices, and they're not necessarily always the same, right? So something like an A100 has a higher price than the 3090, but the 3090 has higher comparative memory bandwidth. So how do you partition this graph, right? This topology of TPUs, or not GPUs, it could be TPUs, it also works with TPUs. How do you partition this into different groups so that you have effectively a prefill pool and a decode pool? All right. Prefill determines the initial response latency, which they call TTFT, while decode dictates the token generation speed, TBT, time between tokens. Okay, so now we've started to introduce some metrics here, right? So we've framed the problem of like, okay, what are the actual different variables that we're trying to optimize, right? Which GPU is doing prefill, which GPU is doing decode, what is the size of the decode pool, what is the size of the prefill pool. And now on the other side of this optimization problem, we're starting to build up some of these metrics that we want to kind of think about. And the survey paper has a nice summary of all the metrics up here. So we just got introduced to TTFT and TBT. TTFT, latency from first input to first token. So that's as soon as I type something in here, right? You can see it was basically a little bit over 4 seconds, right? So there's whenever I hit enter and until I get this first token, right? So that's the first metric there. And then TBT, time interval between consecutive tokens, which is basically, okay, between each of these, how long did it take basically to go from here all the way to the end, right? So for example, when I'm using my edge compute here, right, not only is the TTFT very slow, like when I type enter, it takes a second to get the first token back, but also the time between tokens is pretty slow, right? We have some other ones here, but we'll get to them once we get to them. Let's go back here. All right, let me actually make sure I'm talking here. Question from Open Room. Do you think Cerebrus wafer scale compute will change the inference game? So I think so. You're basically saying there's various startups that are optimizing, trying to improve the hardware versus what we're doing here, which is assume the hardware is already there. How do we improve the algorithm that allocates the hardware to our problem, right? So I think there's gains to be had in both, right? I think that these papers definitely prove that if you have a bunch of NVIDIA hardware, spending time into how to allocate it can give you significant gains. Is there gains in designing the hardware such that it maybe makes this optimization problem easier? Yes, but it depends on how consistent the architecture is, right? right now we're still in this transformer kind of paradigm. You could see a world where we move to kind of more Mambas, more RNNs. You can see a world where we move to a completely different paradigm of kind of deep learning architectures, and suddenly the NVIDIA hardware isn't super useful anymore. So I would say hardware, and trying to optimize the hardware itself, especially because the hardware has a very slow kind of cycle, right? Because you have to design it, and then you have to go get it printed, and then you have to actually get it, put it in the data center, and then actually use it. So it's like years to do that. So it's actually very risky, because you basically have to predict what the inference compute is going to look like before you even know what it's going to look like. So it is kind of a tricky problem. All right. We have a hierarchy of heterogeneous hardware. Okay, that part's important too. So this idea of hierarchy, right? So why are we talking about hierarchy? Why do we add the word hierarchy to this heterogeneous hardware, right? So heterogeneous just means there's a lot of different GPUs, but now we're adding the word hierarchy to denote the fact that actually there's the edges of this graph denote kind of the connectivity speed between them, right? So if you actually look at this graph, right, the way that it's organized, right, is that actually some GPUs are on the same rack, and other GPUs might be on different parts of the data center, or it might even be worse than that, and one GPU is in one data center and another GPU is in a different data center, right? So it's not just the type of GPU, but it's also the connectivity of that GPU to other GPUs within this graph, right? Here's another fancy word you can use: a topological resource tree, right? So a tree is also a graph, right? It's basically a graph that has this kind of like hierarchy to it, right? Where you have the top, and then you have kind of the leaf nodes that expand out, but ultimately it's still a graph. Let's go here. I think they have a better explanation of the hierarchy. Boom, 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 boom. Tens of thousands of GPUs processing trillions of tokens daily. Okay, this goes into the strategy. Let's go into here. Is there anything interesting here? Okay. Hierarchical back pressure determines the scaling actions at the local and global serving instances, right? So as soon as you start talking about local, we introduce this idea of hierarchy within our GPU graph, right? Our topological resource tree. Now we can have different strategies for at the top, or the kind of global level, versus the kind of more tiny local level, right? So like, what are we doing on each individual GPU versus what are we trying to optimize at the level of the whole graph, right? So at each individual GPU, you might be controlling this batch size, right? So at the local instance level, batch size controls the number of requests served concurrently. If a batch size increases throughput a little bit higher, albeit at the cost of latency, right? So what are they talking about here? So what they're talking about here is that there's like one paragraph that I keep trying to find because it's so important. I'm going to find it. I'm going to fucking find this paragraph. I think it's here. Jesus. What am I even doing, guys? Tom Ryzkov. What do you think about HRM, hierarchical reasoning model? We like briefly touched on that a couple weeks ago whenever it was part of the news cycle. But I think mostly people were impressed with the size. Yeah, it beats O3 High on ArcAGI with only 27 million parameters, but it feels like it's kind of overfit to that, right? So I'm not super impressed by it, right? I think there's a long historical precedent of people finding ways of beating very, very specific narrow tasks with tiny models that are effectively just super overfit and have all the inductive biases that work best for that task. So it's impressive, but I don't feel like the HRM necessarily has huge implications, right? It's just kind of like a clever little thing that works on this one thing very well. And again, the idea of hierarchical is like kind of everywhere, so that's not necessarily original either. Okay, here's a little bit more on the topological resource tree. A rack containing multiple GPU types under a single S1 switch is a scarce high-value asset, as it allows prefill and decode roles to be placed on different specialized hardware while maintaining minimal work latency. So you have to have some kind of a priority system, which are logical collections of S1 or S2, right? So they're kind of painting more this idea of like, okay, you have what S1 RDMA subgroups versus S2 RDMA subgroups, right? So some GPUs, if they're on the same rack, they're going to be able to communicate much quicker, right? Think about Jensen coming out with that thing that I think was the new kind of like NVLink thing, or I think it's called InfiniBand or something like that. And he's like, this piece of hardware can effectively have more throughput than the entire internet, right? So that's what he's talking about. He's talking about these kind of like solutions that are generally constrained in space, where if you have GPUs that are relatively close together, the communication speed can be extremely fast. But as soon as you have GPUs that are, okay, maybe this one's in a different room, right? Or maybe this one's in a different data center, then the communication speed is going to drop kind of dramatically. So because we've now separated this LLM inference into prefill and decode, you have to be very careful about the communication between those, right? Because ultimately, your prefill is going to create this KV cache, and then you have to send that KV cache or communicate that KV cache to the actual decoding instance. So if your 3090 is sitting very far away from your A100 that's doing the prefill, then it's going to lead to high latency, right? Because you're going to have to wait, the user's going to have to wait for that KV cache to transfer, and then for that decoding instance to start producing tokens, right? So that TTFT is going to be high. Okay, let's keep going here. Actually, there's one more thing I want to talk about here with the communication. So various GPU types with high-speed RDMA interconnects, right? So I'm going to show this chart here, which I think is important. So this is a little bit less of an issue now, but people are still talking about it, right? So within the umbrella of the whole China versus US narrative, there was these export controls, which are basically regulation that prevent the selling of GPUs to China. And the way that they created these is they basically created these red lines where they said, okay, you can't have something over this level of compute performance flops and interconnect bandwidth, right? And what they ended up creating are these kind of machines like the H20. So you can see here's the H100. That's what kind of most people in the US are used to. They created these weird machines called the H20s that have less flops, but have this very high interconnect bandwidth. And I think that why do we see companies like ByteDance doing all this kind of optimization, splitting up the inference into prefill decode, and then having separate decode pools, separate prefill pools, and having to deal with heterogeneous hardware? Ultimately, that kind of comes from this, right? So if you're an American company and you just have 100 H100s, right? That's a very simple and homogeneous resource graph, right? They're all the same GPU. There's not much optimization to be done there, right? Versus the more heterogeneous your graph is, and the more you have kind of this weird situation where some GPUs have really high bandwidth, some GPUs have less bandwidth, some GPUs are more expensive, some GPUs are less expensive, the more benefit you get from these kind of complicated autoscalers, right? Do you think recurrent neural networks are coming back? I don't think they ever died. I think they're just in hibernation, but we'll see them soon enough. Open room XYZ. Do you think from GPU specification that the can be optimal policy can be basically computed? Or do you see this more as run the GPU and optimize the whole thing while it runs? From GPU specification, can the optimal policy be computed? Kind of, right? So there's two ways to, whenever you have this type of optimization problem, right? Ultimately, what are you doing? Ultimately, you're deciding the value of a bunch of hyperparameters, right? And I think they even mentioned that here. It's very much a hyperparameter optimization problem, right? So you can tune those hyperparameters using real requests, or you can tune them using in simulation, right? So you can imagine a situation where you have a bunch of fake GPUs, right? And you know the metrics for each of those GPUs, right? And then you have a bunch of fake inferences. And then you basically, now that in that simulation, you can optimize these hyperparameters. And then once you've optimized those hyperparameters based on GPU stats and fake inferences, then you can deploy those hyperparameters into your production, right? But I just don't feel like, and then because you now have that simulation, you could theoretically design GPUs that have better or different metrics, right? And then you can use that to design new GPUs. But the problem is that your fake inferences, right, your kind of like mock inferences, are not representative of what the inferences a year from now are going to look like. So if you design a GPU based on simulations that you've made of like, hey, here's a bunch of fake inference requests, and then here's our resource graph, and then we figured out that this specific combination of bandwidth and flops results in a optimal inference per dollar. Therefore, we're going to design a GPU that does that. 2 years later, we might be in a different paradigm where now you have reasoning models, so the average amount of tokens that are produced before you have to send something to the user completely changes that variable. Now you have a weird GPU that doesn't really serve anything, right? So I think this little paragraph here is a good complement to what we're just talking about. This design inevitably introduces numerous hyperparameters, right? In practice, tuning so many interdependent hyperparameters is prohibitively difficult in large-scale production environments, making this approach challenging to deploy reliably. And one additional thing that makes this difficult is that we know, for example, in a similar world, right, which is the training world, right? So whenever you're training these LLMs, you also have a similar problem, right? Where you have a bunch of GPUs and you have to basically spread this training compute over those GPUs in a way that's kind of optimal. It's a completely different problem from the sense of like, what are you communicating, right? So in a training job, you're communicating gradients, you have to kind of send data to all the, so like some parts of it are easier, some parts of it are harder, right? So for example, what's easier about training jobs? Well, you kind of know exactly the data that's going to go in, right? You're basically trying to feed data in and you have kind of like infinite requests. So you don't have this very tricky problem that you have in inference or serving where you don't know what the requests are going to be like when they come in, right? One thing that they show in pretty much all of these, which I think is important to see, is this here. This is daily workload. So you can see here in the x-axis time, 0 to 24 hours. You can see how the number of requests actually isn't the same, right? So in a training workload, it would all basically be the same, right? You're sending data, like you can predict it perfectly because you know exactly what the data set is, you know exactly what you're training on, right? Even if you have a reinforcement learning situation, you know exactly, you have a certain amount of instances that are doing rollouts and creating experience that you can then put in your replay buffer, and then you can pull from that replay buffer. So it's like in training, you have a very good idea of what the workload is, which allows you to solve this optimization problem easier. But for inference, you don't know what this is. You have predictions, you have models that say, okay, well, this is kind of what I can expect on a Tuesday. This is kind of what Saturday looks like, but they're not actually what's going to happen, right? And I just thought these are kind of interesting graphs because they show you really that everybody starts at, nobody's doing anything in the morning, right? So in the early morning, nobody's doing shit. So at 5 a.m., no one's actually requesting anything. And then suddenly, right around kind of the early morning or 10 a.m., right? So when people start getting to work, everybody opens up Claude Code and everybody starts sending requests. Then there's this kind of lull around lunch, right? And everybody goes to eat. The Claude Code's sitting there, nobody's running it. And then suddenly there's this huge bump again where everybody's working in the afternoon, and then another kind of trough, right? For dinner, everybody goes home. And then there's a bunch of people that kind of like to work at night. So there's really this kind of like trimodal distribution here. So, okay, but going back to here, another reason why this is difficult is because, for example, whenever you're picking hyperparameters for model architecture, right? So like, let's say how many heads you have. Here you have 3 heads, right? Why not 4 heads? Why not 5 heads? Why not 2 heads, right? So like there's a choice there. That hyperparameter, the way that you pick it and the way that people generally pick it is they pick it at a small scale. So they're doing these type of hyperparameter sweeps at a small scale, and then it just so happens that whenever you do your YOLO runs, right, whenever you're like, okay, now we've kind of tuned these hyperparameters for this model architecture, now we're going to basically take that same thing, make it bigger, and then just YOLO run and train that big thing, right? It kind of works out. So the hyperparameters that you pick at a small scale extrapolate well to the large scale, right? At least in the terms of architecture hyperparameters, maybe things like data augmentation as well, right? Like how often are you left-right flipping the image kind of thing. But I don't think that works for these, right? So I think that if you have hyperparameters for an autoscaler that you designed for 10 GPUs, those are not going to work well for 1,000 GPUs, right? So this is a hyperparameter sweeping problem that is particularly tricky because of just how inconsistent and unpredictable the workload is, and the fact that the hyperparameters are like very specific to that specific graph of hardware, right? And as soon as you move to a different part of the space of hardware graphs, those hyperparameters are probably not optimal anymore, right? So it's a very tricky problem. Okay. Let's keep going. Vibe coding. Yeah, I don't know how much of the requests are from vibe coding, right? That'd be interesting to see if somebody has metrics of like, in terms of the total GPU burn of humanity, how much of that is code-related agents versus people generating images, right? Okay. Let's keep going here. So they talk about Kubernetes horizontal pod autoscaler. So Kubernetes is basically how people solve this, but Kubernetes was designed before the ChatGPT kind of LLM era, right? So like I said before, like people have been trying to solve these autoscaling issues for a long time, right? Basically since there was the internet and since there was the concept of kind of cloud services like AWS, you started to have this idea of these kind of scalers, and then you started to get these products like Kubernetes that basically allow you to create rules that say, okay, well, if there's 100 people visiting our website, then you have this many servers, and then once the servers start having, once you start having slightly more people that want to use our website, then the Kubernetes will automatically create a new, create a new instance to then take some of the requests off that one instance. So it's like we had solutions, but those solutions don't necessarily work super well anymore. And that's what they're saying here, is that the Kubernetes horizontal pod autoscaler is often driven by metrics like GPU utilization, but this GPU utilization is not really a good metric. It's a little bit more complicated with these inference requests for LLMs, and we need a new solution. And for example, why is GPU utilization not a good metric? Because decode nodes may show high GPU utilization despite operating at the low workload due to KV cache memory pressure. Okay, so the decode nodes, which are the small, I guess not small, but which are the nodes that basically have to get the KV cache and then do the autoregressive, right? So they're kind of like doing one token at a time. They're doing this very compute heavy, right? So you can look at the GPU utilization and say, okay, well, actually, these are being used very well, so therefore everything's good. But it's not good because if you look at the actual final, how much are they actually producing, right? they're operating at this low workload, aka the amount of work that they're producing is low. I'm not even saying that well. Due to KV cache memory pressure, right? So they're kind of bound by memory. Okay. We implement two policy paradigms, two complementary control strategies, a periodic policy for predictable coarse-grain adjustments, and a metric-driven policy for fine-grain real-time optimization. Cool. Periodic scaling policy adjusts resources based on time of day patterns. So you have day-night cycles and weekly patterns. And again, I feel like it's important to note, like, if you, like, why do you want to do this, right? Like, why do you care about, like, if you're buying GPUs, like, don't you already own those GPUs? Like, aren't you already using all those GPUs? Like, why do you need to, like, scale down? Like, what does that even mean? Is your GPU just off? Right? It's not because of the power, right? It's not like, hey, we want to not use these GPUs or utilize these GPUs because we don't want to pay for the electricity. Like, the most expensive part of the data center is the GPUs. So as soon as you have that GPU in the data center, you're burning it until it dies, right? You're running it 24/7 until it basically dies. So the reason you want to scale the size of your pools that perform inference is because all that compute that you're saving, you can effectively either sell or you can use it for your own internal kind of experiments and training, right? So this idea of the kind of spot instance, right? I think they mentioned that somewhere here. Typically, cloud services do not provide rapid links among nodes. Therefore, we disallow tensor model parallel. Okay, that's actually not what I wanted, but it talks about the spot instance there a little bit. Yeah, here's another important point. Mainstream LLM serving systems primarily focus on high-performance GPUs like the NVIDIA A100 and H100 in homogeneous GPU clusters. So this is kind of more to the point that I was saying, that in a lot of these American labs, like, the compute graph that they're using is more homogeneous and all the same GPU, right? Versus in some of these more Chinese labs or academic labs as well, right, where you have kind of a older GPUs, newer GPUs, right? And then you have GPUs with weird configurations like the H20. That's where this type of stuff becomes more applicable. Okay, autoscalers frequently overestimate back pressure at both local and global levels, leading to excessive scale-up actions and resource underutilization. So what they're talking about here is that one common problem that happens with these autoscalers is this kind of overshooting effect, right? So for example, I think this one talks about it the most. No, this one. Yeah, so you have a certain amount of GPUs serving a certain amount of requests. All of a sudden, you get a spike in the amount of requests, and your autoscaler allocates a much bigger amount of GPUs than you even need. And then those much bigger amount of GPUs are just kind of sitting idle after that initial spike. And the best way to understand that is to look at a PID controller. So a PID controller is a control algorithm that is basically part of any robot. Like, this is the most basic controller. And there's three parts to this: the P, the I, and the D, right? So let's say this axis down here is time, this x-axis is time, and the y-axis is kind of the value that you're trying to match. So this is basically like, maybe think about a motor on a robot trying to get to a certain position, right? Or think about one of these autoscalers trying to decide how many GPUs to spin up for one specific request, right? The P part of that, the proportional part of that, is basically, if you crank that up, you'll achieve it faster. So you can see here, when they're cranking up the P, the time it takes to actually get to this value of 1 is less, right? But the problem is that you overshoot, right? So you end up with this kind of thing here where you went past the value, and then now you have to come back to the value, right? And that, the area under here is basically, if you think about it within the autoscaling context, it's basically wasted money, or wasted GPU compute, right? GPU idle time. So the P part of a PID is the easiest way to understand here what they're talking about when they say about this kind of like auto-scaling mistakes. Okay. You can see here's another example of kind of overshooting here, right? So you can see here, there's the request, and then right here, you suddenly get this kind of huge burst of requests, and then the autoscaler suddenly cranks up the number of GPUs, right? So that's what this like kind of stepwise orange line is. And you can see here, look at all this basically wasted GPU hours right there, right? So whenever the background line is over this orange line, people are waiting too long. They're waiting too long to their requests. Their requests are just kind of sitting in a queue, and that time to first token is slow. Or maybe the total amount of tokens, or the time between tokens is also slow, right? But as soon as you have this overshoot, you're wasting. So it's kind of, you're trying to balance this thing constantly. Rapid oscillations between scaling in and scaling out, commonly referred to as flapping. That's what we've been talking about. So heteroscale, which is their scaler, enforces cooling periods in ensuring a minimum interval between the scaling actions to prevent rapid oscillations. Again, think about the PID, right? So what are these, the I and the D, what are those doing, right? So the D is the kind of derivative part, and it basically makes sure that you don't have these oscillations. The I is the kind of more let me actually get, I don't think it's integral and derivative, but PID controller. I want to make sure that I'm saying proportional integral derivative. Okay, it is that. Okay, I was just uncertain. The integral part makes you match it more perfect, but the D there is kind of the more specific one that I want to think about whenever I'm thinking about this cooling period to ensure minimal interval between scaling actions. You also have hysteresis thresholds, which use different trigger points for scaling out and scaling in, creating a buffer zone that promotes stability. Dampening factors are applied to moderate the scale of adjustments. Okay. Sounds like it's possible in the future we might have NVIDIA make two different classes of GPUs, training only versus inference only. Yeah, I think that's already happening. I think you're already starting to see separation of hardware into training hardware and inference hardware. So for example, the training hardware, NVIDIA GPU offerings. The training hardware is being sold kind of as a data center package, right? So like if you're buying something that looks like this, that's for inference, right? That's to put in your computer and then use a model that's serving on your computer. If you have something that looks like this, that's for training, right? But then you're talking about an even further distinction of, okay, things that still look like server racks, but you have server racks that are optimized for training and then server racks that are optimized for inference. That's a bit of a bolder prediction, but because it depends on what the future looks like, right? Do we get a future where most of the inference is happening on the edge, or do we get a future where most of the inference is happening in the cloud, right? It's not entirely clear which one of those two we're going to get, right? Because if distillation works really well and suddenly phone chips get slightly better, then you could very easily see a world where everybody's AI assistant is running directly on their phone or is running directly on their computer, and really the only thing that the cloud is doing is it's doing training, right? Versus you could see a totally different world where the edge devices get thinner and smaller and stupider, right? And then all the inference is happening in the cloud, right? In that situation, you want really good internet, right? Maybe things like Starlink, right? Where you have... you can get internet everywhere. So it's a little bit of a push and pull, very difficult to predict what exactly is going to happen, but hope that kind of half answers your question. I'm only giving half answers right now. How fast do you think they would be if they would design ASICs with some neural networks, say like a diffusion model like Flux? I think they already use models to do PCB design. If a GPU would have more VRAM, you could have two models on them one that you are doing inference and one that you are doing training. That seems pretty crazy. I don't know about using the same GPU for both inference and training. Okay. Let's talk about this PD ratio. The PD ratio is the number of prefill GPUs and the number of decode GPUs, right? So if we decided to split up our GPUs into GPUs that are good at doing this prefill, which is compute intensive, versus GPUs that are good at doing this decode, which is they need more memory, right? Because they basically need to constantly receive and get this KV cache, right? So the optimal PD ratio is not fixed. In our production experience, it spans a considerable range from 1P for every 5D to 9P for every 1D. And again, that also depends on the type of GPU. So like 1P H100 is different from a 1P like 3090. Let's go here. Is there anything else here? Topological resource tree. I think we like kind of talked about a lot of this. Talked about that. Talked about that. All right, let's go into some of these other papers here. At a global cluster level, the number of serving instances determines the overall throughput and latency serving capabilities of the system. An ideal autoscaling policy would dynamically change the number of instances to match the incoming request workload. Right, so that's just changing the resource graph itself rather than necessarily just the hyperparameters of that resource graph. That's the distinction they're making here between the two different hierarchical levels. Let's go to this one. In the prefill phase, a small batch size quickly saturates the GPU's computation capacity. In the decoding phase, the bottleneck lies in scanning the LLM parameters. The throughput increases linearly as the total number of batch tokens rises, highlighting the effectiveness of batching in this phase. This is a nice little graph that shows that. So this is a figure 2 here. You have batch size on the bottom, and then you have throughput in tokens per second. So you can see that for prefill, this relationship kind of flattens out, right? So as your batch size increases, the throughput token per second at some point starts to flatten out, right? Versus decode, it's this kind of more linear relationship here. As your batch size increases, your throughput tokens per second just continues to increase. And this is Llama 7B, with each input having a sequence length of 1024, right? So that's that quadratic, that O of n squared. Continuous batching batches the prefill of new requests with the decoding of ongoing requests to enhance GPU utilization. Here's the same graph. Prefill replicas, decode replicas. We already talked about that. We already talked about this. Traditional implementation of co-locating prefill and decoding phases only leverage standard tensor model parallelism and pipeline parallelism, where only the activations are communicated. In the disaggregated paradigm, transferring the key value cache between prefill and decoding model replicas introduces a significant data movement, potentially creating a communication bottleneck. Okay, so what they're talking about here is there's this idea of parallelism, right? And there's lots of different types of parallelism, right? There's pipeline parallelism. Parallelism is basically taking one blob of compute and then splitting it over 2 GPUs, right? Or 3 GPUs or 4 GPUs, right? So how do you split it, and in what dimension are you kind of splitting it in, right? So all the different types of parallelism are just different ways of splitting that blob of compute that needs to happen over a graph of nodes, right? So for example, pipeline parallelism distributes distinct model layers across multiple devices. So different layers in your model, right? So maybe this top one here, and then the second one is on a different GPU, and then this third one is on a different GPU. Whenever you split it in that way, what is communicated to the different GPUs? Well, this stuff, right? So like these activations. So whenever you have that type of parallelism, what the information that's being sent from one GPU to the other one is these activations. Tensor parallelism splits individual operations or layers into smaller subtensors. So let's say maybe this big FFN here, right? You can imagine kind of this half of it being on one GPU or this half of it being on a different GPU. What else? We got sequential parallelism, which partitions layer norm and dropout activations along the sequence dimension for long context tasks. We have context parallelism, extends this by splitting all layers across the sequence dimension. And we have expert parallelism, which allocates sparse MOE components across GPUs, optimizing memory usage for sparse LLMs. Right? So just different ways of splitting that compute over multiple GPUs. And depending on which way you split it, right, now what you're sending between those GPUs changes. Right? So what they're saying here is that whenever you are doing prefill on one set of GPUs and decoding on a different set of GPUs, right? So that's kind of another type of parallelism if you want to think of it that way, because you're kind of splitting that into two different things now. What you're communicating between that is now the KV cache, right? And because that KV cache grows with the length of your, see every extra word that you add in there, you see how the size of the number of these squares keeps increasing? So because that KV cache grows with your sequence length, the communication can get pretty hairy, right? Between these prefill and these decoding pools, which is why you want to co-locate them, which means basically having them close enough that they can communicate, because maybe you have those like optical switches that are super fast, right? They send information as light, right? Rather than just like a standard like Ethernet cable. So in a heterogeneous setting, each GPU has distinct peak flops, HBM memory bandwidth, and HBM memory limit, right? So that HBM memory bandwidth and HBM memory limit is going to be pretty important if you have to communicate these giant KV caches for a reasoning model that's producing this huge sequence of tokens. Okay. GPU communication bandwidth also varies widely from different NVLink and PCIe generations. Within a server to InfiniBand, which is, I think, the one that I was talking about that has the internet scale communication bandwidth, ROS, TCP, and Ethernet connections among different servers. Graph partitioning algorithm partitions the available GPUs into multiple model serving groups, where each group should be dedicated to serving a prefill or decoding model replica, aka the prefill or decoding pools, and the MaxFlow algorithm guides the iterative refinement of the graph to optimize the model placement. Okay, and this HexGen 2 paper is basically all about this idea of the graph and then iteratively refining the graph. But let's look at this real quick, because I think this was a nice little figure. So this figure 4 shows the communication bandwidth matrix for different settings. So you can see here the color represents the communication speed between the different GPUs in this system. And you can see here purple means slow and then yellow means fast. So you can see here in this first cluster, which they call the homogeneous setting, this is a bunch of H100s, 8 H100s all on the same basically rack. What you end up with there is you see this extremely fast communication between all GPUs. So this makes any type of parallelism very easy to kind of apply, because you don't really need to optimize much, right? It's like it doesn't matter whether you put this part of the model here and this part of the model here and then this part of the tensor here, and it's like you don't really need to care too much about that, because all the communication speeds are all the same, because they're all the same GPU and they're all on the same rack. But as soon as you start going into these heterogeneous settings, right? So here, for example, they have H100s mixed in with L40s, mixed in with A100s, mixed in with A6000s, and those are on different racks. Those racks are potentially different rooms. Some of them are connected via InfiniBand. Some of them are connected with a crusty Ethernet cable. You start getting complicated topologies here, right? You can see some sections here of dark purple, which means very low communication bandwidth. You have some sections here of yellow, which is high communication bandwidth. So you can see how it gets very complicated very quick, and this optimization problem becomes very difficult as soon as you start having these heterogeneous systems. All parallel communications in HexGen 2 are implemented using NVIDIA Collective Communication Libraries and CCL. And this is maybe another kind of like meta kind of point, kind of macro point here, is that it seems like NVIDIA is controlling more and more of this, right? Like traditionally, right? For example, think about that interview that Greg Brockman did, where he was basically talking about in the early days of OpenAI, right? They were doing reinforcement learning and they had PPO as a baseline. And then they basically were like, okay, how do we improve PPO. One thing we could do is we could improve the algorithm. Another thing we could do is increase the scale. Okay, so then he said that really the majority of the engineering in the early days was figuring out how to increase the number of GPUs that you're using for training and for I guess inference. Maybe not inference because they were just running it on a smaller thing, but the TLDR is that a lot of the engineering effort in these LLM labs, right, is basically solving this problem of like, hey, if we keep adding more and more GPUs, we have to solve all these communication problems and this kind of weird graph partitioning and allocation problem. But it seems that because NVIDIA now has a ton of money, right, and because people are buying kind of the amount of data center money that's going to NVIDIA is much higher than the amount of gaming money that's going into NVIDIA. NVIDIA is incentivized to create these kind of like full data centers in a box, right? So basically, you don't have to solve the communication problem. NVIDIA will start to provide more and more and more and more kind of pre-made solutions that already have all the communication and cooling built in, right? Cooling is another big part of that too, right? It's like, you don't have to worry about what cooling you're using. You don't have to worry about the communication because all of that is now being done by NVIDIA. So NVIDIA kind of sells you the whole data center rather than kind of, here's just the GPU, and then you figure out how to connect them all together and solve this problem, right? So I think that's a general trend. Let's see. Effects of batching, we saw that. We read that. Maybe the future will be streaming LoRa's and local inference. Yeah, I like that future. I like the edge compute future the best because it basically is the most private and it puts the individual user in control, right? If all your inference is being done locally, then nobody else is seeing that. And also you can be more certain of the model that's being used and so on. The more of the inference that's being done in the cloud, the more that's abstracted away from you. Now everything that you're doing, all these IoT devices that you're wearing that are in your house, they're all sending all that information to the cloud. So now you can have third parties in between there that can basically read all your data, know all your information. And not only that, but then also the actual model that is being served to you becomes increasingly more opaque. Right, and we saw this with GPT-5, where as soon as they kind of wrapped everything behind this GPT-5 umbrella, you as the end user had less of an, like, you don't even know what model's being run. You know, it's like they're telling, like, you don't know if it's the big model, if it's the small model. So, yeah, I generally don't like the idea of cloud inference being the dominant paradigm in the future. I would prefer if the dominant paradigm is basically edge inference. Okay. We already talked about parallelism here. Tensor model parallelism, pipeline model parallelism. Let's look at this. Neighbor construction. Oh, this is how they take the graph and they optimize the graph, right? So these guys create this optimization problem and then basically iteratively refine that graph, iteratively decide the value for these hyperparameters, which is basically just the connectivity and the grouping of the different parts of this graph or partitioning of the graph. And this is the four things that they do. For example, they flip. A group is originally designated to serve as a prefill replica and it will be changed to a decode replica. They split, randomly selects a split group into two based on a random ratio of GPUs to the first group and the remainder of the second group. They merge groups and then they also move GPUs between groups, right? So this is kind of what the optimization process looks like in real time. You're basically deciding, maybe this is your prefill pool, this is your decode pool. You can see how, like, okay, well, now we're going to add this GPU in there, and now we're going to take out this GPU, we're going to combine these two, and so on. Okay, let's come here. Graph partitioning algorithms partition the GPU into multiple model serving groups. Each group should be dedicated to serving a prefill or decoding model replica, and the max flow, I think we already read that. Did we pretty much do everything here? Are we done? The electricity bill would bankrupt you. Electricity is not the dominant cost here. That's something important to think about. DM 204375 is that the GPU is the dominant cost. That's the most expensive part, right? And something interesting to think about is that faster or the next generations of GPUs don't necessarily use more power, right? So for example, NVIDIA has GPU generations. You have Turing, Ampere, Hopper, Blackwell, right? We are starting, so Blackwell just kind of started to get released, right? We started to see more activity. There was people posting kind of Blackwell builds, and the Blackwell kind of stations, it's not like they use twice as much power or twice as much space as the Hopper or the Ampere generation, right? They actually, it's kind of about the same. So it's like you're getting more performance for the same amount of electricity or power going in, right? So I know that people love to kind of create this kind of like energy power kind of narrative where it's like we're limited by energy and power, but I don't know if that's necessarily like a continuing trend as much as it is kind of just like a one little tiny narrative that we have now, because I feel like we could see we could solve the power generation. We could keep increasing GPU capacity just by improving the GPUs, and each subsequent generation can basically, you can get more compute per watt. I don't know if that kind of makes sense or not. Yeah, I mean, I'm not judging, dude. I don't judge anybody. You know, even if I'm criticizing things, like, it's all love. He has access to free H100. He has access to 100 H100s. I think if you have access to 100 H100s, you're doing something good in life, but also you're probably under a huge amount of pressure, right? Even just like myself, whenever I use like one of those 8x H100 clusters, that's like, and I'm paying with my own money, like, I'm checking on that instance constantly, I don't want to have it sit there and it fails and it's just sitting idle for like an hour. So now imagine that kind of anxiety, but someone who's in control of like a 100 H100 instant. Like, I don't know if you want to live with that anxiety, you get prestige, but it's also a lot of anxiety to live with, to constantly have to make sure that that cluster is working fine and that, it's not just sitting there and not doing anything. Do you think NVIDIA will maintain the monopoly of GPUs for AI? I think they'll continue... Maybe. I had to think about that for a second. I think the Google TPUs are underhyped. If Google sold those TPUs, that could be very interesting. But I don't see anybody overtaking NVIDIA unless NVIDIA shoots itself in the foot. So yeah, if I had to predict, if I had a gun to my head, I think NVIDIA is still the dominant compute provider, at least for AIs and GPUs workloads, AI workloads on GPUs in like 5 years from now. But Jensen Huang could get assassinated or something, and then at that point, like, I don't know what happens. I never found that paragraph that I wanted to talk about. It was about batching. It's probably in this paper. State-of-the-art serving systems. Maybe let's look at these other metrics here. Yeah, because I think we can then go into the paper that kind of like goes deep into these different metrics. All right. What are the other metrics that we can use to determine whether our optimization of the resource allocation in our topological resource tree is maximal with respect to what, right? So what's the loss function here? So, or the optimization goal. It's some blended combination, right? So you can imagine basically it's not a loss function in the sense of like an actual loss function, but you're solving an optimization problem. It's some combination of all of these with weights in front of them, right? And those weights are the hyperparameters that you have to pick. TPOT, average time per token during decoding, measures token generation efficiency. Throughput, tokens generated per second across all requests. Capacity, maximum throughput while meeting SLOs, represents the system's upper performance limit. Normalized latency, total execution time divided by token count. Yeah, anytime you're like normalizing latency kind of seems a little sketch, because when you're normalizing something, right, you're basically taking something with a wide range and then you're kind of compressing it into this shorter range. But whenever you're normalizing things, if you have outliers, right, that can fuck up your normalization, right? So let's say you had a bunch of values over here and then you have one value over here. When you normalize, you're going to kind of, because you have that one outlier value, all the other ones are going to kind of get a little squished, and it's probably not good. And for something like latency, where it's mostly going to be this, but then you're going to have latency spikes, you know? I don't know if you want that, but IDK. Percentile metrics, latency distribution, evaluates stability and performance. Yeah, this is kind of more what I would expect for latency. P50, so you basically are saying, okay, we don't care about the 1% outliers. We're just kind of worried about the mass, the center of the distribution, and making that as small as possible. During decoding, tokens are generated sequentially using the KV cache, which reduces the time complexity to O of n at the cost of increased memory overhead. Right? There's a difference between prefill and decoding. Ooh, here's another interesting thing. Decoding length prediction. Uncertainty in generation length makes request scheduling difficult. Okay. Inter-request scheduling. First come, first serve. Prioritizing an early, lengthy request over a shorter one can delay the latter, increasing latency. Okay, so what we're talking about here is that, let's do this, for example. This is the playground for Replicate, which is how I generated this thumbnail. And for example, let's do this. This is the actual prompt I used. And I'm going to go here, and there's the Black Forest Labs Flux 1.1 Pro. So basically, there's an instance somewhere that Replicate has that's probably already loaded. So because enough people use this Flux 1.1 Pro, when I hit run model here, there's already an instance that is running this model, right? So if I just click run once, my request is now getting put on some queue, and it's being combined with other requests that other people have, and then all of those are being performed in a batch, right? Because by doing it in a batch, you basically increase the utilization of that model being served, right? But now, as soon as you have that notion of a queue and a batch, now you have these hyperparameters, right? Like, what if I click this 4 times? And then I wait 5 seconds, and then I click it again, right? So that was a really weird pattern of behavior where, okay, if I clicked it 4 times, then those 4 are obviously going to probably make sense to do them in a batch. But do you wait? How long do you wait to see if there's another one that comes later, right? So do you send those 4 through the current batch, and then you get the next one on the next batch, right? If there's 100 people using this, then you kind of get a much smoother input, right? You can kind of take the batch size and okay, there's always going to be at least 32 people that want this image generation model, and that means that this batch size can be kind of more consistent, right? But if less and less people are using it, I probably want to wait a little longer, right, to fill up my queue and then do a batch rather than kind of immediately, as soon as I get the request, doing it, right? So this idea of kind of like the queue and the like waiting, right? So do you prioritize the early lengthy request over a shorter one? that can lead to, this is less of a situation because in this case, this is an image generation model. So you know the exact generation length, right? You know that every single time it's going to take this much time, right? You know the exact amount of compute that's going to happen per request. But now inside this reasoning paradigm, right? Or even in the text paradigm, right? You don't know what the request length is going to be. So you need to be careful where, hey, if someone asks you a very complicated question that's going to take a very, very long time, you don't want someone who's just asking like a short question where the generation length is going to be short just to be waiting, right? So this is where the idea of uncertainty, and as soon as you have this, generation length is an important parameter to determine some of these other hyperparameters, such as like how long are you waiting in the queue, like what's the batch size, then being able to predict that now actually becomes useful, right? So here they have a bunch of different papers where you're trying to predict how long that generation length is going to be so that you can more efficiently kind of batch them and prioritize them in your inference. OpenRoom XYZ, you are absolutely crazy with these. You're like slapping on the keyboard. Batch processing. Translate all the books on the planet to all the languages to generate audio transcripts seems ideal for batch processing. Yeah, I mean, that goes back to what we were talking about with training versus inference, where if you have some job like that, where you're like, hey, here's like 100 books and I want to turn these into audio for my audio generation model, right? Maybe it's like one of those data cleaning pipelines or those data generation pipelines, synthetic data generation pipelines. Those are easier in terms of this kind of mapping compute to the hardware problem because you know exactly what what's coming in, right? You're like, okay, well, I have 100 of these books and I know the exact model. I know the exact generation length that's going to come out. It's all predictable, right? I already know what it's going to look like. I know what my workload is going to be. Versus an inference, you don't know what that workload is going to be because Replicate doesn't know whether I'm going to click this 4 times and then wait and then click it once, or whether I'm going to click it once and then wait and then click it 4 times, right? XAI doesn't know what question you're going to ask and when you're going to ask it, right? So that uncertainty is really what makes this problem a difficult optimization problem. Quantization-based compression reduces memory by shifting from high bit to low bit precision. So this is yet another potential vector or kind of dimension of optimization, right? Where, hey, you have this GPU graph. What level of quantization are you using at what GPU and at what time, right? So imagine we're back in this world, right? And we have a bunch of requests coming in over the course of the day, right? You can imagine that something that would be optimal to do is that right here in this peak, right? And OpenAI probably does this. They probably start serving a higher proportion of heavily quantized models, right? So the quantization is kind of like a continuum where it's like a discrete continuum where there's like 32, 16, 8, 4, right? But you could say, okay, well, if I know I'm going to get a huge amount of requests right here, I'm going to start spinning up these instances that are serving a quantized version of my model, and all the requests that are kind of simple, shitty questions that are very easy to answer, I'm going to route them into those instances that are now serving that quantized model that's fast and cheap, right? So that's why they're talking about that in this survey paper, this idea of like, okay, maybe you can actually choose the quantization level based on what you can expect in this workload. To reduce LLM deployment costs, spot instances are used despite preemption risks. I think we've already talked about spot instances, right? But this is basically the whole idea of like, if you have multiple people using a cluster or a compute graph, then there's going to be situations where someone else's autoscaler deallocates and now there's an empty GPU and you can then use that empty GPU, right? So that's this idea of spot instances, which is like GPUs that are only available for some chunk of time. So your autoscaler is not just interacting by itself, it's also interacting with other people's autoscalers and then AWS's autoscaler itself, right? So there's like multiple different, it's almost like an ecosystem of different scalers that are all kind of interacting with each other. It's kind of weird to think about that. If you have infinite batch that works, you can do background on the same nodes. Infinite batch. Efficient storage management is critical for RAG system, particularly in handling large KV caches. So if you have a retrieval augmented generation system, right, where you now not only have a KV cache that is sitting in memory, but you also have kind of external information that is sitting in memory. So now you need to be able to pull that as well. So as soon as you have a RAG system, you start to become memory limited as well, right? Where it's like, okay, well, how fast can you pull that relevant information to then add it to this context to then auto-regressively generate the next token? Which is part of why I feel like RAG is becoming less and less relevant, is because it just adds this whole layer of complexity, right? The retrieval process in that RAG acronym adds a lot of complexity to something that's already pretty complex. And we're getting pretty good because of reasoning models with things like very large KV caches. Also, a lot of the coding agents, the way that they search for things is like they literally like grep, they find. So I feel like tool use, model-directed tool use is easier than some kind of like RAG system where you have something else that goes and then searches this database and then brings back things, and then the model's just kind of sitting there waiting for this thing to come. Maybe they're more similar than I think they are. I don't know. Sometimes I feel like RAG is dead. Sometimes I feel like it's actually just the same as what we're doing now. Expert load balancing. Agentic workflows come into the play in long batch. There'll be a lot of capacity that can be used for fast responses. I've heard people, so for example, like I've heard people that are leveraging the fact this right now, right? So because, here's the story. Because the workload is time dependent, right? It's on this kind of diurnal cycle, right? If you wake up and do all your coding work from zero, or from like basically midnight to 4 a.m, you know that you're much more likely to get requests into a model that is probably bigger, right? If you're sending 100 requests at 4 a.m. in the morning, there's not a lot of other people that are competing with you, so you're probably getting those requests on the actual big model. Versus if you're sending requests at like 9 a.m. in the morning, when everybody else is sending your request, the likelihood that your request is being routed to some quantized model or some smaller model is higher, right? So I've heard of people that are starting to basically game this, and basically they do all their programming at like weird off hours, right? So that they don't get the slop. So that's something to think about as well, which wouldn't happen in the future where all the compute is happening at the edge, right? If all the compute is happening at the edge, then it doesn't fucking matter when you send the request because the model's on your computer and you're just running the model. But when you live in this world of like cloud inference in batched requests, and then model providers secretly quantizing, making you smaller models, if your query doesn't include the think hard about this, right? They'll just route you to some shit model. Like, let's go back to here though, because we were talking about mixture of experts. Here we go. Mixture of experts. allocates active experts to GPUs and others to CPUs, pairing high and low load experts using historical data. High load experts are identified using deployment statistics and periodically duplicated to optimize performance. So a mixture of experts, one way to think about what it is kind of like another form of parallelism, right? You're basically deciding to put these experts, right, which are basically different versions of this, right? You see this little MLP block here. What a mixture of experts is like, imagine there's basically 2 more of these here, right? So then anytime you go through here, you basically either go through this FFN or you go through this FFN or you go through this FFN, right? And each one of those FFNs is one of the experts. And one of the benefits or one of the reasons why MOE became so popular is because you could basically put experts on different GPUs, right? So GPU has expert 1, GPU 2 has expert 2, GPU K has expert K, right? So it's like a kind of easy way to parallelize that, right? If you're using it all on one computer, generally the way it works is that the experts are on the CPU, right? So like whenever you see the number of active weights, it's like there's stuff that's being stored on your GPU memory, and then there's stuff that's being stored kind of on your CPU memory, which is like the RAM, right? Or even the SSD, right? So there's kind of like a hierarchy of memory in a computer, right? The closer you are to the actual chip, that's the most premium spot. So only the best stuff is there. And as you move kind of further away into the cold storage of your SSD, that's where you're going to keep the like low value experts, the experts that don't get used that often, right? And I've explained this expert stuff before, but I always think it's important to have this in mind when you think about mixture of experts. This is a figure from the Mixtral of Experts paper where you can see which expert is being used at each individual token. And I just think this is an important figure because it really just shows you how you're using a lot of different experts, which makes a lot of sense because whenever you're training these mixture of experts models, you're often explicitly regularizing to use experts evenly, right? So if your model over the course of training starts to use one expert much more than other experts, that's actually not very good. You want it to be basically as even as possible, but even when you make it as even as possible, you're going to have this high traffic expert and low traffic expert. So for example, here in this, you see how there's obviously one expert that's kind of all about the indentation, right? You have another expert that is about, I don't know, it's hard to pick them, but it seems like this green one is about the like dot, but then sometimes the dot is the red expert. Kind of hard to know what each expert is doing. It's not very understandable by humans, but this red expert kind of seems to be used more than whatever this like dark blue expert. So therefore, inside your topological resource tree, which is just my favorite way of calling these graph of GPUs, you might want to allocate more GPUs to high load experts, right? So periodically duplicate those experts and then have some service that basically trims the low traffic experts and stops serving them. Actually, here's a very nice little diagram of what I was talking about. When you're doing it locally, right, you have your GPU VRAM, right? Maybe you have 80 gigabytes of GPU VRAM, right? So you're going to have only a subset of the experts, expert M and expert N. Then on your kind of second tier of the hierarchy, you're going to have your CPU memory, right? Your RAM, and you might have other experts there. And these experts can be kind of quickly loaded into the GPU because they're right there in the CPU RAM. The CPU can very quickly grab them and put them into the GPU. Then you have the third layer, which is your SSD, right? Which is your kind of cold storage, right? And part of the, and then extremely low use experts can sit in that SSD. And then if you need to use them for some reason, now you need to pull them up into the CPU RAM and then pull them up into the GPU. So it takes even slower. You see 6 gigabyte per second, 16 gigabyte per second, and then 50 gigabyte per second between those, right? And this here is not and this is not one machine. This is 2 GPUs, right? So for example, maybe you have one of those like GPU link things that basically allows GPU to GPU communication to be very fast. Let's see. primary challenge, and let's read the conclusion. So sometimes with these survey papers, like the conclusions are actually usually pretty good, you know, because with these non-survey this one I still like because it's basically ByteDance is a actual team that's actually serving lots of requests on lots of GPUs. So like I love these papers because it's like people that are in it, you know, they're like truly at the frontier, they're truly doing the engineering, and I'm just super happy and glad that they're willing to share all this information with us. These survey papers, they're interesting because these people understand it more, right? So like the reality is that even though, right, if you're one of these people writing this paper, you might not necessarily be as aware of the landscape of this as someone who like did a survey paper. So the survey papers, sometimes they're a hit, sometimes they're a miss, but at least the person who's writing these has read more papers over LLM inference serving than anybody else, right? So like the conclusion that they write is the conclusion of someone who's read more papers in this niche than anybody else. So that's why I feel like the conclusions are generally good for this. Let's see. The primary challenge in LLM serving is the significant memory requirements caused by the scale of the parameters and the computational load associated with attention mechanisms. We present a thorough and hierarchical review of the methods, blah, blah, blah. We explore small yet significant areas. Okay, so basically they went through all this shit and they said, what is the fundamental problem here? So here's a million different papers, and ultimately it's just this attention mechanism. Like, why are we doing all of this? What the hell is all this? You know, why are we doing all these complex optimizations and topological resource trees? Well, it's ultimately just this, the attention mechanism and the significant memory requirements. Everything is downstream from that, right? It just boils down to the fact that whenever the way that we currently do artificial intelligence, when you're doing token by token by token with these autoregressive transformers, the memory and compute of building this thing here, right? This attention, right? These steps right here, bloop, bloop, bloop. That's what it is. All right. I don't know if I have necessarily anything else to say here. Anti-flapping, we already talked about that. I think I had some heteroscale showed 26.6 percentage points increase in GPU utilization and 9.2 percentage point increase in SM activity. SM is the streaming multiprocessor. It's basically like the CPU of the GPU, right? So in the GPU, there's like a little chip that's actually doing all the work. That's the SM. Hundreds of thousands of GPU hours are saved a day, which accounts for money. I think that's pretty much it, guys. I don't really have much else to say here. I'll answer some questions, and then I'll do a little summary. Ilya, so much engineering put into RAG with these graph and synthetic data to understand it is dead. So I think what RAG is ultimately doing, which is taking information from some other place and bringing it into the context of your LLM, that as a concept is not dead, right? Whenever Claude Code uses grep to search your directories and find a specific piece of text in a file, and then it brings that into the context of your language model, that is effectively RAG, right? That's what it's doing. It's retrieving something and then using that retrieved piece of text to augment or improve the generation of subsequent texts, right? But what is dead about RAG is the way that RAG was originally framed. So in the original RAG papers, a core part of that was this idea of having your text, right, your database of text that sits outside your LLM indexed with these embeddings that were kind of semantic-y, right? So you basically have a huge, think about like a book, and then every page in that book, you feed that page of text into a model, and that model creates a vector or an embedding that basically gives you a representation of the semantic content of that page. And then you could index a database using that. And then what RAG was really all about was basically optimizing the process of taking the current taking the current context, searching your database of previously indexed content, finding the high semantic similarity hits, and then putting those into the thing, right? And I think that part of it is dead, right? This whole idea of like maintaining this database with the like indexed by the embedding, like that's what's going away now, but it's being replaced by the model just literally searching with a grep or a find tool in that database itself, right? So like the database is no longer stored in these weird chunks indexed by the embedding. It's now just stored in text form, and then you just like Control F the thing, right? So like RAG, in terms of like what the original high level concept was, is definitely not dead, but RAG as a specific engineering trick, I think is dead. Let's see, Open Room XYZ. Combine MOEs with a bank of LoRa's. Okay. How do you expect real-time neural games will become a reality and run on consumer hardware? I think the neural games are coming pretty fast. I've seen, like, obviously, Google has the whole Genie stuff, but like I think I've seen at least one other startup that is doing that. So I think you're going to have a situation where a couple different startups start to release these neural games, and then that puts pressure on kind of the more foundation lab players to like hop into the category, right? So it's kind of like what you saw with the coding agents, where as soon as Claude Code had this, and Cursor had this kind of success with the coding agent format, everybody rushed to clone it, right? And now we live in a world where we have like every single foundation lab has their own kind of Claude Code clone. So I think something similar might happen with the neural kind of generated games, where you're going to see a startup, maybe two startups that release something out there quickly. One of those is going to go viral. People are going to start using it. And then all of a sudden, every single frontier lab is going to have a version of that. Right? So that would be my prediction. Programming demo scene kind of shows current limit of compression. People are just love this idea of compression. I don't know. I'm kind of a believer in the whole, what is it? Computational irreducibility, right? Where there's certain things that you just can't compress. And those are almost the things that are the most beautiful. Okay. I need to go here. I need to go. Let's do a summary. Autoscaling inference. All right, so this stream, we talked about autoscaling inference, mainly centered around this paper here, Taming the Chaos by ByteDance, where they talk about their autoscaling framework on their 1,000 GPU cluster. Because there are tens of thousands of GPU cluster, because they are a Chinese lab, they have the unfortunate reality of dealing with a very heterogeneous compute graph. So they have a lot of different types of GPUs with different strengths and different prices, right? So therefore, the auto-scaling that you can kind of naively get with things like Kubernetes, or that you can naively implement in the case of more homogeneous compute graphs, don't work very well. So you're seeing, and these papers are kind of proof of a kind of a type of very complicated and nuanced optimization problem that deals with how to spread the unknown workload that is determined by a bunch of weird factors such as kind of diurnal cycles and time of day, and it's also a combination of what models are available and what models people find useful, right? Like the workload of generative art, right, is going to be very different from the workload of reasoning models. It's going to be very different from the workload of a generative game, right? So trying to find the optimal way of matching the available GPUs and the GPU types to the specific workload is basically an optimization problem that we're never going to solve. There's never going to be one way to do it. There's going to be a million different possible ways to improve it, dimensions of measuring performance and improving performance. Everything from TTFT to TBT to TPOT, different ways of measuring the user experience with that model and how efficiently you are serving it. So, yeah, that's pretty much it. These papers are just basically all different ways of thinking about that problem, different dimensions that are solvable with different algorithms. But because this is such a multifaceted optimization problem, like the waves of time are going to just erode this in a year, right? So like 1 year from now, all the conclusions that they draw in here are going to be basically null because you're going to have a completely different type of landscape, completely different type of workload. The GPUs are going to be different, so... But I think it's always interesting to read these type of papers because they kind of show you a snapshot in time of like, hey, this is the stuff that we had to deal with. This is the stuff that we found was useful. And we're already starting to see kind of this idea of a topological resource tree. Something about that, I love saying that, but this idea that your compute is never going to be in just kind of one central thing. It's going to increasingly be more and more kind of weird, and just like you're going to have like one data center here that has this generation, and then you're going to have like a decentralized network of these things, then you're going to maybe have compute in space, right? Like imagine 10, 20 years from now, a world where the inference server is in space, because the cooling is easier, and then the solar panels are more efficient up in space. And if you have satellite internet with things like Starlink, then why not put your GPUs in space, right? Then you can increase the latency would be better, right? You don't have to, if you're sitting there in the middle of nowhere and you have a cell phone and you send an internet request, right? It has to go up to the Starlink satellite, then back down to the data center where it gets served, and then back up to the Starlink satellite, and then back down to your cell phone. Versus like imagine if the satellite that you're communicating with for internet purposes also has a GPU on it, right? Now that can be a lot faster. So how cool is the topological resource tree going to be when some of your nodes are in space? All right. That's all I got to say. Hope you guys found this interesting. Thank you, AWISP, OpenRoom XYZ, Ilya, DM204375, Max Malley, Jai Kai, who else? Tom Rizkov, Majetti, Ed, Fabio, Wanjun, Mark B, and James McLean. I appreciate all of you. Thank you for this. Thank you for being viewers of the stream. Hope you have a great weekend, and peace.